In this video, I would like to share with you some of my final touches and checks that I perform on PCB designs close to the end of a PCB design process. So pretty much right before or very close to before I start generating manufacturing and assembly data to then send to my manufacturer. This might include topics such as copper pours, voiding in planes, transfer vias, doing checks of the silkscreen, solder mask, and so on. You can think of it as somewhat of a PCB design checklist, but again, it's more of a final touch segment, and we'll see what that means throughout this video. I do plan on making a video on PCB design checklists, so have a full process for the schematic, PCB design, layout, and routing sections. But again, this is a more condensed form, closer to the process of what I do near the end of a PCB design. So hopefully something slightly different. The reason I'd like to talk about this, for example, for the board you're seeing here, is that we want to try and get our PCBs to work, of course, for the most part, the first time we have them produced and manufactured. A board like this, which is fairly intricate, quite a few layers, and not too inexpensive to produce, we don't really want to have to respin many times. So therefore, we'd like to pay a bit more attention to certain aspects throughout, of course, the whole PCB design process, but also towards the end. Now, if we Google PCB design checklist, not entirely what this video is about, you'll see many different topics and articles about various checklists you can do, for example, mechanical checks, drill checks, component placement, routing, and so on. And of course, all of these should be adhered to right from the get-go. So you should keep in mind good PCB design practices, make sure to always check with your mechanical team, make sure your schematic is correct, your pinouts are correct, and so on. Again, this isn't the focus of this video. The focus of this video, again, is to give you somewhat of an insight into what I would look for at the end of the design, assuming I have followed all of the typical PCB design checklists. Again, this will be a topic for a future video, having a full PCB design checklist. A huge thank you to PCBWay for sponsoring this video. The board we're going to be examining in this video, I'm actually currently having produced by PCBWay, and I'll do a full PCB design walkthrough for that board in a future video once I have it in my hands. Make sure to check out PCBWay's services. I in particular use their advanced PCB design service quite a lot because they offer not just normal through-hole boards, but also HDI, so with micro vias, buried and blind via boards, up to an incredible 60 layers, and many different custom options, for example, impedance control, custom stack-ups, and so forth. They of course also offer PCB assembly, and I have all of my PCBs also assembled by them. If you haven't already, make sure to follow them on Instagram to check out what designs they're producing and what their assembly and manufacturing capabilities are. A huge thank you also to Altium for sponsoring this video. I'll be showing you these PCB design checks in Altium Designer, but of course these are ECAD tool agnostic. But if you would like to try out Altium Designer for yourself, make sure to go to altium.com/YT/Phil's Lab, and you can get yourself an Altium Designer free trial with Altium 365, as well as if you're interested, you can get 25% off your first license purchase. With your Altium Designer free trial, including Altium 365, you can check out all of the cool Altium 365 features, such as mechanical co-design, which will be important for PCB design checks as well, library management, supply chain management, and more. To help you out with your part search, make sure to check out Octopart, which scans across many different manufacturers, vendors, distributors, and so on, to help you find the exact parts you need for your design. For all of these, I'll leave links in the description box below. Let's get started with going through some PCB design final touches and parts of a PCB design checklist. Again, this is not an exhaustive list. I would like to highlight some points that are not typically found on, for example, online PCB design checklists, and something I like to do for myself as well. The board we'll be looking at is called this A-scope board. It is essentially half digital and half analog. It's effectively an audio analyzer based on an AMD Xilinx Zinc system on chip. We have some external memory, Ethernet, powered by USB, has USB high speed and so on, various other memory and so forth. We have this completely isolated analog section with ADCs and DACs, and it's a fairly intricate 8-layer design. Of course, the starting point should be to check the schematic thoroughly, make sure that the pinouts are correct, that your functioning is correct, that it fits your overall system requirements, and so on. We won't be going into detail here. In terms of PCB design, of course, I try to follow PCB design best practices, use impedance control where needed, spacing, layout as appropriate, keeping distances to minimize crosstalk and so on, choosing good layer stack-ups and build-ups and so forth, and these are things we will not be covering in this video. Again, this is more of a final touches video. Please refer to the PCB design checklist for more information on these other points. In any case, if you're a sole designer or if you're part of a company, it really pays off to have someone else design check and review your design. Some of these designs may take several days, several weeks, and sometimes even several months to complete. And when you're so in this design, it's hard to take a step away and see the design with fresh eyes, and that's why other people can help in that regard. Something very simple, of course, first of all, is to make sure that the schematic and the PCB design are synchronized. All of the information is the same between schematic and PCB design. We have the same parts, we have the same designators, the same netlist, and so forth. So what I'd always do, also during the design, anytime I make any changes to the schematic, is import the changes from the schematic, make sure there are no differences between the schematic and the PCB design. This is also very important when exporting a bill of materials. If you've changed designators or if you change manufacturer part numbers and so forth, you want them to be consistent between schematic and PCB. If you're pouring signal layers, then also with copper pour, for example, attaching that to ground like I've done here on the top layers and pretty much any signal layer in this design. So layer 4, layer 6, layer 8 are my signal layers, and I've also filled them with ground as well. There are a couple of things to pay attention to when you do this, when you arbitrarily, so to speak, pour copper over the remaining or free areas on your design. One thing is that, for example, for controlled impedance nets, such as the ones we see here, these rather thin traces, which are data and address lines between the DDR3 memory and the AMD Zinc system on chip. We have to make sure that our copper pour has far enough clearance away from these traces as to not impact the impedance profile by too much, unless, of course, you're doing a coplanar structure. Typically, the minimum space you should leave, and you can add, for example, design rules, the minimum space you should leave between the trace and the copper pour is 3 times the distance between the signal layer and the next reference layer. So, for example, for this microstrip traces, so on layer 1 and layer 8, I would need at least a 3H, so H being the thickness of the dielectric, spacing to any copper pour, and that's why you see quite a bit of clearance also here between these controlled impedance traces and this copper pour. So that's one thing you should pay attention to. Also, what you have to pay attention to is make sure you have copper balance, preserve somewhat of a copper balance when these ground copper pours, for example. So we have a large ground copper surface area here, which has quite a large thermal mass, for example, compared to this short 3.3 volt connection we see here to this capacitor. And we want to make sure that the thermals are balanced either side of the pad, and that's why we use these thermal relieves. So make sure you have copper balance and thermal balance in your design when incorporating these copper pours. Additionally, because we have all of these copper pours and these ground fills, so to speak, on pretty much every one of these layers, and I do, of course, also have internal ground layers as well, 3 of them, what we need to do is stitch these together with vias at adequate spacing. So you can see I have a lot of these ground vias spaced around the board, also around the perimeter of the board, that stitches all of these copper fills, these ground copper fills and copper pours together. This is important because otherwise little patches of these copper pours can act as antennas, they can resonate. So by tying them down at fairly regular intervals, depending on the maximum frequency in your design, and which relates to the wavelength, of course, we can tie these down with these stitching vias. I can recommend this article by Zach Peterson on stitching vias, and I'll leave a link to this in the description box below if you'd like to learn more. What I also suggest you do, and you can also ask your manufacturer to do this, is if you're pouring copper, somewhat arbitrarily let's call it, is to clean that up and not just pour it over the whole surface and not care about how it's poured and so on. For example, if you have small islands that are not connected, or sometimes under inductors, you might not want this copper to flow directly underneath. Depends on the situation. What you can do is add in, for example, these polygon pour cutouts to clean up the copper pour. And you can see I have various of these copper polygon pour cutouts. You can see it's this dashed red line on the top layer, and I have various of these segments along the board. If I add that in and then re-pour the polygons, you can see those areas are then not affected or not poured by this copper pour. For example, this region here, for this top polygon pour of ground copper, we might want to use a copper pour cutout in these small sections to clean this up, because this copper pour here isn't really adding very much. It's not tied to ground by a stitching via nearby, so you might want to clean that up. And that's something you can ask your manufacturer to do as well. You can see I have this on inner layers as well, just making sure I'm not leaving too large unstitched areas, and by using these small sections of polygon pour cutouts just to shape this overall polygon pour, this ground copper pour, just a bit more. On the topic of planes, and for example this ground plane on layer 2, we can see due to, of course, our through holes, these might be from vias or they might be from plated through hole pads, for example for connectors, we're getting these voids in our ground plane. Now, this is of course pretty much unavoidable unless you're using specific PCB manufacturing techniques, but for these basic through-hole designs, we're going to always have these cutouts. And for example, under the BGA, there might be quite a lot of these cutouts, and then we only have these very small slivers of copper going through. So for power delivery, this might be problematic if we have a lot of these, just very thin slivers. So where we can, what we want to do is of course increase the area of our copper pour and only neck down through these little necks where we have to improve our power delivery, make sure we can handle the current, we improve our inductances and so on. Another way we can help with that is by placing our vias and our pads appropriately. So for example, going to our ground layer, we can see from the output of this 1.8 volt regulator, I'm using several vias to improve power delivery, inductances, and current handling capabilities. So I'm using several of these 1.8 volt vias in parallel. I've spaced them like this because you can see I can get copper slivers of my ground planes to flow through and between these voids. Now, if I move my vias closer together and then repour my copper planes, you can see these voids, so to speak, have joined up. And this is not what we want. If we can, I want to space my vias further apart, so at least get some slivers between these voids or between these vias. That will improve my return paths and so on. So make sure you check out your ground planes and your power planes for these slivers. Make sure, if you can, space your vias further apart and so on. And this is something you can fine tune during the design, of course, but also make sure to check that near the end of a design stage to make sure you haven't voided your planes too much. What's also important to do, and oftentimes in design reviews I don't see people doing this, is to remove unused pad shapes or non-functional pads. So for example, under this BGA package, I'm fanning out with this dog bone shape. So if I drop a via, then I'm, for example, going to layer 6 and routing to wherever I need to go to, I'm not actually using that via or those via pads on other layers. So you can see here, I still have the via pad, but it's not connecting to anything. So my power and my ground layers, I have all of these via pads that are pretty much just taking away space and they're not really necessary. In addition, these via pads add, so to speak, unnecessary capacitance to that net, which might degrade signal integrity. So what we can do, once we've routed out our design and we're pretty much happy with it, as a somewhat last step, I will go to Tools, Remove Unused Pad Shapes, and I can do this both for vias as well as for plated through-hole pads. Click OK, and now you can see on, for example, this ground layer, we have removed the pads, but of course we've kept the plated barrel of our via, so this plated through-hole. For example, if we look at the layers where we actually are routing out from that via, we can see these pads are preserved. So only where we don't need them, where they're not connected, we then remove those unused pads. Now I haven't repoured my polygons yet, so these, for example, this ground fill, I can do that by pressing TGA in Altium Designer, repouring all my polygons. And because we have different clearance constraints between pads and holes, you can see I've actually improved my polygon pore structure here because I now have larger slivers between these cutouts, these voids, due to my vias and my via holes. So I have a specific design rule which requires a certain distance between the hole and copper pad and a copper pore, for example, and this is now improved because we've gotten rid of the pad. So there's many benefits to removing these non-functional lands or removing unused pads. And you can see that on all of these different layers. So for example, my power layers are less cut up now as well, and I have less of these smaller slivers and so forth. Another point I typically add in my designs these days are what's known as teardrops. Let's see the design before we add teardrops. For example, looking at this RJ45 jack, we have these very thin controlled impedance traces going to these rather large through-hole pads with the RJ45 connector for a part of my Ethernet differential pairs. Similarly, we might have something on a smaller scale going from a signal trace into a via or out of a via, or generally, of course, going from an SMD component to a trace. We have these right angle shapes of copper, for example, for these pads going from a trace into this pad, and we have this somewhat small impedance discontinuity here at this interface, and of course for these through-hole pads we have a larger change in area going from this trace, for example, into this pad. Now from a manufacturing standpoint, we try to avoid any of these right angle shapes, but also it can in certain cases help by having a smooth transition from a narrow trace width to a wide pad by adding in a transition. That's what we call teardrops. We can add teardrops globally by going to Tools, Teardrops, and this should be available in most ECAN packages. And I'll just leave the defaults now. And now we can see, for example, the transition from our trace to our through-hole pad is smoothed via these teardrops. And now you can see where the name comes from. We are smoothing this transition going from narrow to wide rather gradually. And we can change the parameters of these teardrops and so on. Same thing, for example, trace to pad or trace to via. We can see when you have these smooth transitions, we don't really have these right angle shapes, which helps with manufacturing and also eases the impedance discontinuities, so to speak, and makes them more gradual, even though that has a lesser effect in most cases. Once you've placed your teardrops, make sure to repour your polygon pores. And then also to double check your design rules by running a design rule check, because sometimes these teardrops, especially in very cramped areas, can violate the clearance constraints and you might have to adjust the teardrops on a case-by-case basis, so make sure to do that. In multi-layer designs, we often have multiple ground planes, and ground planes or power planes can act as return paths. So for example, we have ground on layer 2, layer 5, layer 7, as well as all the copper fills. So for example, layer 1, all of our signal and power traces have a reference directly below, that is layer 2, and that's where our return path will be. For AC signals above a couple of kilohertz, for example, if we look at the output of this crystal, of this CMOS oscillator, this trace, the return path will be directly below on that ground plane. So you want to ensure that we have a solid return path and a reference path below ground or power, for example, as in this design. Now, when we are switching, for example, signal layers, for example, if we're going from this Ethernet physical layer through this series termination resistor through our via, we're actually transitioning from layer 1, where we have a return path on layer 2, or a reference plane on layer 2. We're transitioning from layer 1 to layer 6. Not only does our forward path, so our signal layer, change from layer 1 to layer 6, but our return path, or our return planes or reference planes, change from layer 2, being a microstrip, to layers 5 and 7 as our ground returns. So with a signal via, we get our signal going through this transition from layer 1 to layer 6, but what happens with our ground return path? Given that we're going through, for example, a signal via, and then we have to go through the board to get to layer 6, what happens with the return path? Now, without any vias nearby, this is actually pretty much poorly defined because we're traveling in the Z dimension. We're going from our return path being layer 2 to our return path being layer 5 and layer 7. So what we should add are what's known as transfer vias. So it's a grounded via that provides a close local return path during that Z-axis via transition. So we have a signal via in our Z-axis and we have a return path. This ground transfer via placed close to our forward signal via to make sure we ease that reference, to make sure we have a defined return path when changing from layer 1 to layer 6, for example. And this also happens for layer 1 to layer 8 or any time we change reference planes. You can use one of these transfer vias also for multiple signal vias if you're particularly space constrained. But this is something I would try to add and find space for, of course, during the design, but checking that also during my final touches, during the final steps of my design review. One more thing to check with, for example, through holes is to check if they're actually plated or not. So depending on the ECAD tool you use, if a hole is plated or not, for example, if I go to this JTAG connector, click on one of these pads, open the properties section on the right-hand side, and scroll down, go into the pad hole, I have this small little checkbox which tells the tool if this hole is plated or not. And of course, this will then change your manufacturing file export or not. Now, I got bitten by this once where I had accidentally deselected this plated checkbox. And in 3D view, or just looking at the pads themselves, not looking at the barrel, it might seem like this is a plated through hole because we have a pad or this exposed pad on the outside. But we also have to look inside the barrel, and that's something I didn't do at the time, which then wasn't plated and it got manufactured with a pad but not with a plated barrel. So if I deselect plated and then look at 3D view again, we can see the optic has changed a tiny bit, but of course that might be hard to spot if you've got many other parts in the design. We can't really see that that's non-plated. So make sure that the holes you want plated are actually plated and checked in that design. One thing that should also be added to PCBs are Fiducial Markers, and these are effectively to help the automatic optical inspection tools and also for alignment and positioning of components. Fiducial Markers come in various different shapes and sizes. For example, here we might have a plated copper pad, so an SMD pad, and we have a solder mask pullback where we have no solder mask around that plated pad. So we have this high contrast area, which is very easy to pick out by automatic optical tools on a PCB. On a real PCB, this is what this might look like. You can see we have this high contrast area with no solder mask and a plated exposed copper pad. These aren't tied electrically to anything, typically. What we typically want are global fiducials, so that's at least 3 spread as far apart as we can on the board. So in this board we see here, we have one top left, and bottom right. These are these global fiducial markers, but we can also have local fiducial markers, which might help placement of fine pitch components. So that might be around BGA packages. We might have a local fiducial marker here, or QFNs and so forth. Typically, these will be these round fiducial markers, but sometimes you will also see, for example, these crosses as fiducial markers, as I have on this board. So I have 3 placed where I can, fairly widely spaced apart. Of course, you can make them slightly smaller if there's space constraints. So I have 3 on the top because I have SMD assembly on the top, but also because I have SMD assembly on the bottom, I also have 3 fiducial markers here. So 1 on the bottom left, and then I have 2 on this right-hand side, spaced as far apart as I can reasonably get them on this PCB design. The reason I use crosses here is because I actually stole this idea from NVIDIA. If you look at some NVIDIA GPUs or GPU PCBs, you'll see they use crosses as fiducial markers. Now, there actually isn't any particular benefit to using crosses. I just thought they look cool. On other designs, for example, this set bread here, you can see I've used round fiducial markers, so one here on the right-hand side, bottom left, and then at the top here. But I'd strongly suggest adding these yourself. Of course, you can let the board house do that for you, and they'll probably add that on a panel in any case. But I'd strongly suggest adding in these fiducial markers. And if you have larger, high pin count, fine pitch components, make sure to add local fiducial markers as well. Silkscreen is something that should be checked and added some final touches to before you proceed to generating your manufacturing and assembly files. Importantly, for example, for Silkscreen, so in this case, this white text on the front and bottom side of the PCB is that the silkscreen isn't overlapping copper like so, because if this does actually get manufactured and the manufacturer doesn't remove the silkscreen over the copper, this can result in assembly and soldering problems. So make sure you keep your design rules. There will be design rules where you have copper to silkscreen clearance, and make sure it's adequately far away depending on your manufacturing constraints as well, given by your manufacturer. In terms of text height and text sizes, you would typically want a minimum of 1mm text height and a stroke thickness of about 0.15 millimeters as a very rough rule of thumb, but again, check your manufacturer for their capabilities. If I can avoid it, I also try to not place my silkscreen directly on top of holes. So for example, like so, you can see the C is now above the via hole. Now with tented vias, this is not too much of a problem, but it doesn't look that great. So I typically also try to place my text. Of course, this is not taking into account tolerances, not directly onto holes, and especially if they're exposed holes. Again, this is the whole copper clearance thing as well. Same thing goes text to text, so we wouldn't want, for example, our silkscreen to be something like so, to try and keep adequate spacing between silk and silk as well, silicon components and so forth. Always add pin 1 indications, so that's to ICs, or if it's to connectors, or for example CMOS oscillators, or diodes as well. Either add a plus where the anode is, or a line where the cathode is, and tell your assembly or manufacturing house how you've designated your pin 1s and your anodes and cathodes on your polarity markings. I also like to include, for example, rough outlines of components and connectors on my silkscreen, and this helps assembly just a tiny bit. Also, for example, for these BGA or QFN pads, this can help if you're, for example, manually aligning them, manually soldering them, and maybe add some useful labels, for example, what these connectors are, what these LEDs are, and so on. I also like to add maybe some sort of logo, of course, the title of the board, a revision, maybe a version number, date, initials, website, and so on. And you can, of course, also add in QR codes, serial number boxes, and so on. But I typically like to also add in these 4 hash marks, and then tell the manufacturer, please add the date code, for example, week and year, where this symbol is shown, and this will be in my manufacturing drawings, for example. Another important final touch and check you should do is that of adjusting the solder mask, that is the solder mask openings, and checking for appropriate solder mask clearances. Solder mask is applied over the copper foils of the PCB. After etching, this protects against contaminants, it can prevent solder ridges and so forth, and typically you'll see that on PCBs as this rather green color, but of course you can choose different solder mask colors and so on. Now the solder mask process has limitations as well, so therefore we have design rules and design constraints for the solder mask as well. And this will depend on the type of solder mask that's being used and how it's being applied, and that depends of course also on the manufacturer as well. There are a couple of parameters to look at when looking at solder mask. For example, if we have a pad, we're going to have a solder mask opening around that pad, and as well as some clearance between the copper of the pad as well as where the solder mask begins again. And this is because the solder mask, of course, isn't perfectly aligned, and you might have some movement in the solder mask, and we don't want that to overlap that exposed pad. Therefore, we need to keep some sort of clearance around pads. And your manufacturer will tell you what those clearances should be around pads, and that might depend on the color as well, which is important to know, and of course the process type. So here we can see PCBWay for green has different parameters to red, blue, white, and black. So for green, we actually have smaller clearances, so 50 microns, and red, blue, white, and black has 75 microns. So that's one parameter you want to set up. In our design rules, that's typically known as the solder mask expansion, and you can set that to whatever parameters your PCB manufacturer allows. Now you can also leave that up to the PCB manufacturer and communicate with them, and simply set the solder mask expansion to 0. Now if we look at the pads, we can see the solder mask is, at least in the ECAD tool, perfectly aligned with the outline of the copper pad, of the exposed pad, and then we can let the manufacturer adjust based on their processes and based on their knowledge of their design process, which might oftentimes be the best thing to do. However, I actually like to manually define my solder mask openings and communicate with my manufacturer. So I'll typically aim for slightly above the minimum of what the manufacturer suggests as my solder mask opening. So as you can see here, this is about 50 microns. So I'm leaving a tiny bit of gap between my exposed copper and the start of the solder mask. Another parameter we need to look at is then also the bridge width. So if we have, for example, a QFN package or a QFP package, we'll have solder mask slivers, or hopefully we'll have solder mask slivers or bridges between those individual pads. Now you can't make those bridges arbitrarily small. There are minimums depending on the PCB manufacturer and the process they use. So for example, for PCBWay, for a green solder mask, we have a minimum bridge width of 100 microns, but recommended is 125 microns. And for other colors, that is a bit larger as well. We can see those bridges, for example, underneath this QFN package. These are the bridges between these pads. So we have our solder mask opening, but then we also have these bridges between those pads. And those need to be larger than a certain amount given by your PCB manufacturer's capabilities. Again, the design rules. We can see that under the design rule of minimum solder mask sliver. And for PCBWay, for the advanced services, you can also get away with about 0.1 millimeters as a minimum sliver, but oftentimes that might be 0.15 as a minimum. So now if we go to the top solder mask layer in 2D view, this is a negative layer. So anytime you see shapes, this is where solder mask is removed. So we can measure the distance between the solder mask openings, and we can see this is about 0.14 millimeters, which is okay if we have a 0.14 millimeter clearance, but if we have a 0.15 millimeter clearance, this will be a design rule, and our PCB manufacturer will probably have to adapt our files. So there are several ways of going about this, and some parts and packages you probably will not be able to hit those bridge constraints. What you can do, again, is just let the manufacturer adjust, or let me just do this very crudely. I can press P and then fill. I could, for example, fill in with solder mask opening between those pads, and then in 3D view, we have removed the solder mask around those pads. Now, this is typically okay. With a proper assembly and solder paste printing process, the chance of getting a bridge between these is actually comparatively small. But if you can, I would strongly suggest leaving bridges between these pads. But if you can't, and if the solder mask bridges are too small, you might have to remove the solder mask or create this solder mask opening between these pads as a fix. Now, we don't have any solder mask bridges, but this might be slightly worse for soldering and yield performance. But this is something you can keep in mind, but always talk to your manufacturer about this. Very important aspect, especially if you're designing for example, a product that needs to sit in an enclosure, what generally is always the mechanical aspect of a PCB design. And this should pretty much be thought of before you even start layout and routing. You might have a predefined board shape, you might have connector positions and placements that are very specific to that design. These are some things that should be double checked with, for example, a mechanical engineer, or if you're doing it by yourself, exporting the step files, checking that with the enclosure, checking that you aren't violating any constraints, for example, overlapping components, or if you're plugging in connectors, you might want to add those into your design and make sure that the shrouds of those connectors don't interfere, and might be easy for you to get your hands in and to pull these cables out or plug them in and so on. And this should of course be thought of throughout the design, but make sure to double check that at the end of the design. Also, for design for manufacturing, design for assembly, we want to make sure that our components mechanically aren't particularly close, not just from an electrical standpoint, but of course mechanically, because we have these pick and place machines, they need to have space to pop these components in. We might have tolerances in component placements and so forth. So make sure to keep all of that into account and keep good clearance between all of your components and devices, and to do mechanical checks throughout your design. You might also want to add in your enclosure. So depending on your ECAD tool, you might have some basic 3D modeling or model capabilities where you might add in the enclosure just to verify and do sanity checks. For example, how well the PCB sits inside of the enclosure. Does it hit the edges and so on? Now, of course, this is somewhat eyeballing it, but just having a 3D view available has helped me many, many times just spotting maybe simple mistakes or where I might see some clearance issues rather than running through a full mechanical CAD program, which you should do in any case. Something that can be forgotten as well is to repore all of your polygons in the design. So for example, in this multi-layer design, we have various copper pores, for example, the power planes internally, or just ground pores to fill in, so to speak, the voids on the signal layers and so on. And it's important that you repore all of these polygons before you export, before you run your design rule checks. So I can go to Tools, Polygon Pores, Repore All, and make sure you run that before you run your design rule check, just to make sure your board is up to date. What I'd also like to check is go to Tools, Polygon Pores, and then Polygon Manager, because also sometimes the pore order is important. For example, I have various polygon pores on layer 1, but I also have these ground fills, which I want to do as a last step around all these other polygon pores. and I want to have these smaller polygon pores rather than this blanket, so to speak, ground fill on the top layer, on the bottom layer, and so on, take precedence. That's why I've moved my ground pores right to the bottom so they're poured last, so we have a higher priority for these other polygon pores and so on. So this is something you should verify, because sometimes polygon pores will pour first before other polygon pores and you might not get the expected results. So make sure to check that out in the ECAD tool that you use. What you should be doing during the design, and also of course at the end of the design, is confirming your design rules via design rule check. So for example, in Altium Designer, and this isn't available in any ECAD tool, we can go to design rules, and this is where we've set up, for example, our clearance constraints, we've set up width constraints, solder mask expansion, and so on. And these should be set, of course, depending on what manufacturer you're going with, or to specific standards. Once you have those in place, of course, and this should be done right at the start of a PCB design before you do any layout or routing. Once you have these design rules in place, we can then do a design rule check, for example, going to Tools, Design Rule Check, and then running the design rule check, so comparing our design to what rules we set out. And at the end of the design stage, when you're getting ready to prepare your manufacturing files, you shouldn't have any design rule errors. So you shouldn't have any clearance constraints, any unrouted nets, short circuits, or any of these design rules you set up shouldn't be violated. So it really pays off to set up your design rules properly with respect to what your manufacturer capabilities are. You can get your PCB manufacturer's capabilities either by just messaging them or going to their website if they have that, and their PCB capability section will tell you what design rules you can design to. And keep in mind, you shouldn't design to any minimums unless absolutely necessary, but you should go above those minimums to give yourself some leeway and to ensure you might get a higher yield during the PCB manufacturing and assembly process. So these are the steps I would naturally encourage you to do throughout the design while you're placing sections, while you're routing out sections, to make sure you're staying within these constraints and don't have to clear a lot of design rules at the end of the design. Another thing is, of course, the 100% routing completion. Sometimes with a lot of nets in the design and just purely looking at the rat's nest, it can be hard to spot if some connections are not routed out yet. For that, I go to Reports, Board Information, scroll down, Routing or Routing Information, click Report, and hopefully we should see we have no connections remaining. We have 100% routing completion. And that's of course what we want to make sure we haven't missed any nets. What I'd also strongly suggest, just to give yourself a different view and a different perspective on your design, is before you're generating your final manufacturing files, is of course look through 2D view, make sure that the planes all look okay, you're not getting, small slivers, that the traces always have a reference plane, so on, you're not crossing splits, the usual things. But what's also very helpful is, of course, as we saw before, looking at the 3D view, and this can help, for example, quickly detect if we have overlapping silkscreen on copper, sort of eyeballing clearances and so forth. But what I also find really helpful is simply doing a very basic Gerber file export, because that gives me a different perspective on the design. So I could go, for example, to File, Fabrication Outputs Gerber, or whatever file format you prefer. And for this, we're just doing a simple quick check. And then using, for example, in Altium Design, the built-in CAM tool or the Gerber Viewer, this just gives me a completely different perspective, or somewhat of a different perspective on the design. For this, I will typically go through all the layers, so I'll go through my copper layers, but I can also look at the silkscreen, solder mask, and everything that will later then be exported and sent to the manufacturer. And again, this is not something entirely new, but it gives me more perspective on things. So for this, I can, because all the color has been stripped away, so to speak, I can see, are the slivers okay? Am my voids okay? How do my thermal reliefs look? Do I have some weird overlapping structures? Things like that. For example, if I zoom into layer 3, you can see this via maybe here is causing this disconnect of this polygon pore below. So maybe I could move this via up, and something, to me at least, some things are easier to see in this view, or just again give me a different perspective. You can also put layers together, for example, looking at solder mask layers or paste layers, making sure your pads and your paste, for example, for the stencil openings, are properly defined where you want them to be. So I definitely suggest going through this process near the end of your PCB design process when you're about ready to generate manufacturing files, because again, this gives you a different view on things. A big part of also of checking your designs and verifying your designs, and this is actually also part of my final touches, so to speak, is double checking all of the footprints that I have in my design. So that's making sure the mechanical dimensions are in order, and of course the pads as well. So for example, for this exposed pad QFN IC here, which is part of USB physical layer IC, I need to make sure that I matched, for example, the suggested footprint from the datasheet to what I have on my actual PCB. I can either do that by simply comparing to the datasheets, of course, which is quite manual and tedious, and that's how I usually do it. Also when creating my footprints, of course, but there's a very quick and very efficient way of also triple checking this, so to speak. And typically I'll just export very preliminary Gerber files. So even if your routing isn't complete, you can export your Gerber files, just export a bill of materials and a pick and place file. So those three assets you need, Gerber's, pick and place, and bill of materials. And we can then use that in an online tool to check our footprints, for example. I'm not at all affiliated with EuroCircuits, but I do always use the footprint checking tool, which you can use for free when you upload your files to their website. So I'll leave a link to this in the description below. But once you upload your Gerber files, pick and place, and bill of materials, they will analyze the PCB for you. But they also have a PCBA visualizer, which is great because this allows you to check your bill of materials, make sure your parts matched up with your designators, how many parts you need, and so on. But they also have a section to check the footprints and so forth. So if I go, for example, to the check, we'll have to rotate some footprints and so on, but you can actually go through, for example, assembly issues to see where components might not match up and so on. You see there's quite a few things already popped up here. But this is because some of the components aren't rotated correctly. This was just a very quick export of the Gerber files. If I go to the component placement editor in this tool, I can click on various components in my design. It'll jump to that on the PCB and it'll show my lands compared to the footprint EuroCircuits thinks we need from the datasheet and from their inventory, from their system. So the red outline is the footprint they would want, for example, and the pads underneath are what is in my design. And this is incredibly useful, especially for more complicated parts, maybe this QFN. If I click on this QFN, we can see, for example, the orientation of the part. So they've marked pin 1 with a slightly thicker red trace, and I can, of course, rotate to make sure that matches up and so on. I can check my footprints, my pad outlines, and so on. This is very useful also for connectors. So if I select this connector, we can see this needs to be rotated by 180 degrees. So I can rotate that, and then I can center the part to roughly check if this matches up. Now I haven't quite centered it, but I can roughly check if this matches up with the relevant footprint. And this is something I pretty much do with every single design, just to make sure, are my footprints correct? Am I getting any errors here? Is it what it's supposed to be? And I've actually caught some of my own errors using this tool. So I can really strongly recommend this. And again, I'm not affiliated with EuroCircuits in any way, shape or form. This is not an advert. This is a generally useful tool that I use all the time. I also think it's very important to generate manufacturer and assembly drawings and documentations before you get your PCB manufactured and assembled. Even though a lot of times these days PCB manufacturers don't really insist on it, I think it's a very useful tool to convey meaning, intent, and information that's required to make your board functional. These could be, for example, fabrication notes. So, for example, if you're designing to or fabricating to a certain IPC standard, what solder mask colors you want, what thicknesses you want, your layer stack-ups, dimensions, and so on, would all be contained, for example, in a PDF document, or you can do that as a separate Gerber layer or layers. This would include, for example, your stack-up information, so maybe a typical build-up you're aiming towards, and of course you can ask the manufacturer to adjust that stack-up and so on, impedance control requirements and so forth, drill tables, and of course assembly information and assembly drawings for top and bottom and so forth, just as a very basic bare minimum information. And this is something I definitely generate because this improves the chance of your PCB being manufactured and assembled correctly and according to your specifications. If you'd like more information on this, please check out the video on my channel number 94 on how to get your PCB manufactured and assembled, which goes into a bit more detail. Thank you very much for watching this video. I hope it was helpful and I hope it gave you some insights into what you might do when you're coming close to the end of a PCB design process, adding in some final touches, maybe certain things to look out for. Again, this video isn't meant to be a complete PCB design checklist. This will be a topic for a future video. If you like the video, please leave a like, a comment if you have any questions, and don't forget to subscribe to stay up to date with any future hardware design, PCB design, firmware, and DSP videos. Thanks again, and I hope to see you in the next video. Bye-bye.